Okay, let's look at 4.3. This is really going to be the last main section that we're going to cover in Chapter 4. 4.4, I've decided we're just going to, not going to really cover that. I may put there's only 3 homework problems I wanted you to look at, and I may put those up anyway. We'll see about that. But really, 4.3 is going to be the last section that you're going to be tested on for Exam 3. So, first thing we want to talk about in 4.3 is a very important theorem, and it's called the mean value theorem. And it's a very intuitive theorem. In other words, it seems like it should be true just by looking at a picture of a typical graph, which is what they're trying to get you to do on the top of page 279. So let's just take a look at what we mean by the mean value theorem. So suppose we have some function, and it looks like that. And if I just pick any 2 points that are in the domain of this function, say A and B, and I'm going to draw the secant line. So here is B comma f of B, and here is the point A comma f of A. I'm going to draw the secant line between those 2 points on my curve. Now, what it says basically is that there's going to be at least one point where the line tangent to the curve at that point between A and B is going to be the same as the slope of these two, of the secant line here. So in other words, I should be able to find at least one point, it looks like it might be about right here, where the line tangent, so this is going to be my line C here, the line tangent is going to have a slope, which of course is going to be the derivative, f prime of C, that's the slope of the line tangent, and that's going to be the same as the slope of this line right here. What's the slope of this line right here? Well, it's change in y over the change in x. So f of b minus f of a divided by b minus a. And so all this is saying is that there does exist some c. You pick any 2 points on a function that's differentiable, and you connect those 2 points with a straight line. Well, the slope of that line is going to be some value given by f of b minus f of a over b minus a. And you're going to be able to find some value c in between those 2 points, such that the slope of the line tangent, which is to say the derivative at that point, has the same slope as that secant line there. So that's all that says. So it says that we have that c such that f prime of c is equal to f of b minus f of a divided by b minus a. Could be that there's more than one point. In fact, here it looks like there may be a couple. It looks like maybe this point right here might have a point in there where we have a tangent line that has the same slope. So it could be more than one point. The mean value theorem says there will be at least one point, so that's true. All right, next thing we want to talk about then is what's called the first derivative test. And so we talked a little bit about how to find where a max or min occurs by finding critical values. Remember, critical values are places where the derivative is either equal to 0 or the derivative is not defined. Well, remember that the value of the derivative tells us something about the original function. In particular, we said that the first derivative test, increasing-decreasing test, said a couple of things. First of all, it said that if f prime of x is positive, what did that mean? That means that f of x is increasing. So a positive derivative, and we should use some notation here. I'll use an arrow, so that means implies. A derivative positive implies that the function's increasing. And also, the derivative being negative, that'll be true. If that's true, then that means the function is decreasing. So we're going to use this information to determine whether or not we have a function that is a max or a min, or a critical point that's a max or a min. In other words, we're going to use this information here to classify a critical value as a max or a min. And this is what's called the first derivative test. Let's look at an example using the first derivative test. So I'm going to pick one out of the book here. Let's just go ahead and take a look at number 7. Number 7, you're given a function f of x, and it's equal to x cubed minus 12x plus 1. And the instructions there at A, B, and C: find the intervals where it's increasing and decreasing, find the local max and min values, and concavity and inflection points. We'll get to that in a minute. But first of all, what I want to do here for this function, all I want to do is I want to find the critical values, sometimes called the critical points, and classify those as either local max, local min, or it's possible, as we talked about last time, that a critical value could be neither a local max or local min. Remember the example of that was f of x equals x cubed, where we have a derivative of 0, but it's not a max or a min at x equals 0. Alright, so first thing we're going to do is find the critical values. So that's the first thing we want to do. And remember, we're going to do that by taking the derivative, setting it equal to 0. So f prime of x is going to be 3x squared minus 12. And notice that there's not going to be any points where our derivative is undefined, but we can set it equal to 0 and solve that equation. So we're going to get that 3x squared is going to equal 12, which means x squared is going to equal 4, which means that x is going to be plus or minus 2. So I have two critical points. Two critical values, one at positive 2, one at negative 2. So now what I do is I want to classify these as either maxes or mins. So what I'm going to do, and I'm going to do it a little bit differently than the book does it. I'm going to make a real number line, and I'm going to look at my two critical points, negative 2 and positive 2. Let's remind ourselves what the derivative was. The derivative of this function was 3x squared minus 12. Alright, so what I'm going to do is, down here, I'm going to look at f prime of x for these regions here. And basically, for any number in these regions, the derivative is going to have the same sign. It's either going to be positive or negative. For example, if we take a number to the left of negative 2, let's suppose we take f prime of negative 3. We know f prime of negative 2 is 0. F prime of negative 3, that's 3 times negative 3 squared minus 12, which is 3 times 9 minus 12. What's 27 minus 12? We don't really care what it is. It's 15. What we care about is whether it's positive or negative. Alright, so that means any value to the left of negative 2, any value smaller than negative 2, the derivative is going to be positive there. Alright, so for that whole interval, the derivative is positive. Now, what about for values in between these two? Well, here we'll take, let's do it in a different color. Let's do it maybe in a lovely shade of green. F prime of 0, that's the easiest value to pick between negative 2 and 2. That's 3 times 0 squared minus 12. That's negative 12, less than 0. So we're negative here. Alright, so that whole interval, you pick any value you want between negative 2 and 2, the derivative is going to be negative at that point. Now let's try something to the right, the easiest thing to try. To the right of 2, something bigger than 2, probably 3 is the easiest. 3 times 3 squared minus 12, that's going to give us the same thing we had before. 27 minus 12 or 15. Again, all we care about whether it's positive or negative. It's positive here. Now, what does that tell us? Well, remember that if the derivative is positive, that the function is either increasing or decreasing based on those. Well, the derivative is positive, the function is increasing. So the function's going up here. Derivative is negative, that means the function is decreasing. So we're going down on this interval. Derivative is positive, that means the function is increasing. So I don't know what my function looks like necessarily, but it's going to have this sort of shape to it. Alright, so now I can see where I have a max or a min. Negative 2, since we are going up to the left and down to the right, negative 2 is going to give us a local max, and positive 2 is going to give us a local min. So we're going to have a local max of f of negative 2, whatever that is, at, well, that says where it is, local max of f of negative 2, and we'll have a local min of f of 2. And if we look at a graph of this function here, we're going to put it in, it's x cubed minus 12x plus 1 again. You can see we do have a local max at negative 2. It's way up here. F of negative 2 is a pretty big number. We have a local min at positive 2. F of 2 is a pretty big negative number. So a local max at negative 2, local min at positive 2. That's where they occur, and the actual local min and local max values are the function evaluated at those points. So we would say we had a local min at negative 2, local max of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Looks like 17. If f of negative 2 is 17, which I think it's going to be, that's negative 8 plus 24, 16 plus 1, yeah. So we have a local max of 17, and it occurs at x equals negative 2. We have a local min of whatever this point is here. What's this point? It's like negative 15, maybe. Well, I can't see what it is. Yeah, negative 15, that occurs at x equals 2. So we could state our conclusion like that. Now, so we saw the intervals in which f is increasing and decreasing also, by the way, right? F is increasing between negative infinity and negative 2, decreasing between negative 2 and 2, and increasing from 2 on out to infinity. So f of x is, what we say, increasing on that interval negative infinity to negative 2. It's decreasing on the interval between negative 2 and 2, and it's increasing again on the interval from negative 2 to positive 2 to infinity. And we saw that in the graph as well. Now, there's another way to classify our critical points, and that's what's called the second derivative test. So I want to look at that as well, and then we're going to start looking at some examples, I think. The second derivative test, remember that the second derivative tells you something about the original function as well. Remember that if f double prime is greater than 0, then f of x is what we said is concave up. Alright? If f double prime of x is less than 0, then f of x is concave down. Alright, now this is going to help us here, because suppose we have a critical point. So let x naught be a critical value. And so that's going to be a place where f prime then equals 0. That's what we mean by critical value. We'll say it's a place where the derivative is 0, not necessarily where it's undefined. Well, if, let's see, if f double prime at that critical value is greater than 0, what does that mean? Well, if the second derivative is positive, well, we're happy about that because that means we're going to be concave up. And if we're concave up, we have this shape. The only place that we could have a critical value would be sitting at the bottom. So if that's the case, x naught is going to be a local min. All right, it's going to be a spot for a local min. All right, well, if we take the second derivative at our critical point and it comes out to be less than 0, well, if the second derivative is negative, we're not happy about that because that means that we're concave down and the only place that a critical point could be is sitting at the top. So that would mean that x naught is a local max. So if the second derivative is negative at the critical point, you have a local min. If the you have a local max. If the second derivative is positive at the critical point, you're concave up, so you have to be sitting at the bottom, and you're a local min. So let's go ahead and look at number 7 again using the second derivative test. Remember our function was x cubed minus 12x plus 1. Our derivative, f prime of x, was 3x squared minus 12. We set that equal to 0, and you'll recall we got x to be plus or minus 2. So we had 2 possible critical points. Now let's take the second derivative. F double prime of x, well that's just going to be, looks like 2 times 3, which is 6x, 12 is a constant, so that's it. Well, if we take f double prime of positive 2, we get 6 times positive 2, which is 12, which is greater than 0. And so what do we say? Well, the second derivative is positive, that means we're happy about that because we're concave up. And so we have a local min at x equals 2. What about f double prime of negative 2? Well, that's 6 times negative 2. That's getting ahead of myself there. 6 times negative 2, that's negative 12, which is less than 0. Not happy about that. That means we're concave down. Means we're sitting on top. That means we have a local max at x equals negative 2. Exactly what we had said before. I like the second derivative test. It's a little slicker. Although that first derivative test will give you a little bit of information about the about everything. Let's do one more thing here before we start looking at some examples. Let's look at this program here. Again, this is the TEC. I don't know what that stands for, but it's actually, if you have a disk, if you got a new book, you should have a disk in the back of your calculus book, and you put that baby in, and you'll be able to see some pretty cool software for some of the concepts that we talk about. 4.3 has a program that we can look at. Now, notice what we're given here. We're given the function of the derivative. This is f prime of x. And what we're going to do is we're going to enter information about this, and from that we want to draw the graph of the original function. So first thing we're going to do is we're going to list maxima. Where is f a max based on what we see? Well, let's see. You know what? Maybe we'll start down here with where is f increasing and decreasing. F is going to be increasing wherever f prime is positive. Where is f prime positive? Well, from here to here, right? That's where our derivative is above the x-axis, so the derivative values are positive. So we're going to click on that from here. Let's see. Let's undo that. It missed it. I want to go from here to here. Is that what I want to do? Let's clear that. It's not. We have to go through an order, I think. All right, so maximum first. All right, so here it's negative, so that means the function's decreasing. Here it's positive, so it's increasing. So going down, then going up. Well, let's see. How about here? Here we're positive, so the function itself is going up because the derivative is positive. This is a critical point. The derivative is 0 here, so we have a critical point right here. And to the right of that, the function is decreasing since the derivative is negative. Alright, so here is going to be, should be a max right here. Alright, so we've labeled our maxima. How about minima? Well, we have, here's a critical point where the derivative is 0. Here's a critical point where the derivative is 0. Alright, what does that tell us then? Well, let's see, over here, the function is decreasing to the left, increasing to the right. So we're going down and then coming up. So this must be a min. And same thing with this critical point. The derivative is negative to the left and positive to the right. That means the function is decreasing to the left and increasing to the right, so that must be a min as well. Alright, now we can go ahead and hit our increasing intervals. So we're going to be increasing wherever the derivative is positive, so from here to there, okay? And then we're also increasing from here on out to infinity, because the derivative is positive there, it looks like. Now where is the derivative decreasing? Well, it's going to be decreasing wherever where is the function itself decreasing? That's wherever the derivative itself is negative. Well, the derivative is negative from our leftmost point to this first critical point, where the derivative is 0. So that means the function's decreasing because the derivative is negative. Even though the derivative is going up, it can get confusing. It's negative all throughout this region. So the function must be decreasing because the derivative is negative. Now in this section here, the function is increasing like we said. Here the derivative is negative again on this interval. So if we mark off from here to there, on this interval the derivative is negative, so the function must be decreasing. Alright, now what we're going to do is we're going to go to the second derivative and try and get some information of our function based on the second derivative. Okay, yeah, this is something I forgot to mention here. Inflection points are where the derivative is equal to 0. So let me go back here and say that real quick. F double prime of x equals 0. If we solve that equation, that gives us inflection points. And what inflection points are basically is where the graph changes from concave up to concave down. If I have a function that looks like this, I'm going to have an inflection point roughly about right here. And you see to the left of this, my second derivative is going to be negative. I'm concave down. If you poured water on this, it would spill off. Whereas to the right of this inflection point, I'm concave up. If you poured water in here, it would hold water. So where I change from being concave down to being concave up, I have an inflection point. So at this point here, at this value of x, if this is x naught, f double prime of x naught would equal 0. Now what's true about this point here? Well, this is where our line tangent is the steepest. You look at our line's tangent here, notice that our derivative is decreasing because we're concave down, and it's going to be the steepest at this point, and then it starts to flatten out. So the second derivative, where it's equal to 0, where we have inflection points, that's where the derivative is the steepest. Alright, let's go back to our graph. Where are inflection points? Well, this is the graph of the second derivative, so we're just looking for where it's equal to 0. There's a spot, and there's a spot, so we have those two inflection points. Now we're concave up wherever the second derivative is positive. Well, the second derivative is positive in this region, so we'll go from here. Oh, wait, clear that. So let's see, I got to go back to my inflection points are here and here. Now let's look for concavity. Concave up all the way back here to this point. Now between these two inflection points, the second derivative is negative. That means we're going to be concave down. From here on out, we're going to be concave up because the second derivative is positive. Concave down, again, is going to be in between these 2 points. There you have it. Okay, once we're done, we can click on the Done button here. And what it's going to do then is it gives you 20 seconds to graph the function f of x. You need a function that's going down here, going up here, going down here, and going up here. So you have a max at this point, a min at this point, and another min at this point. Concave up on this region, concave down on this region, concave up on this region. Alright, so time's up. So hopefully you graphed one. Here's what the graph looks like. Here's the original graph f of x. So again, it's decreasing here to this minimum point, increasing to this maximum point, decreasing to this minimum point, increasing here. So that makes sense with our first derivative. Our second derivative tells us that we're concave up in this region. Then we have an inflection point about here. This is where the derivative is the steepest, where the graph is the steepest, where the derivative, I should say, is the highest, because the graph is the steepest. And then it concave down in this region. We have another inflection point right here. Again, so the graph is the steepest at this point, and then concave up from here on out. Alright, here's all three functions together. So the blue, remember, was your derivative, and the green was your second derivative. So look at those and make sure that all makes sense. Alright, we'll look at some examples in the next video.